thank you for joining me today for our webinar presentation on the subject of using biodiesel in cold weather. I am Eric Bjornstad. I'm the Technical Information Director with Bell Performance in Central Florida. And here in Central Florida, we do not tend to worry too much about cold flow problems. This December, this is 2017. This past December 2017, in the last half of the month, there's an Arctic cold snap hitting much of the United States, except for us down here in Florida, where it was 72 degrees at Christmas time. But we also know that because we've been formulating cold flow treatment packages for diesel fuel and biodiesel for many years, we know that once you get above Florida, that's where the market starts. And so it is a worthwhile topic to discuss today. And so the focus of what we're going to be doing today is we're going to be aiming to give you a good foundation on understanding the issues of what happens with biodiesel fuels in cold weather. So we're going to be covering aspects of why biodiesel fuels gel. We'll talk about the best practice options that are available for solving this problem, and we'll discuss some operational recommendations on how to handle and how to work with biodiesel fuels in winter environments. In other words, we're going to talk about the hows and the whys about biodiesel fuel gelling and what you can do about it. So if you're up north, you know full well that when it gets cold enough, you have to be concerned about diesel fuel gelling. All diesel fuels contain wax or paraffin components as part of their composition. And when the ambient temperature drops below a certain temperature, the waxes in that fuel become insoluble, and they form crystals that lead to the fuel thickening and gelling. Of course, part of the reason we're here today is because we know that biodiesel fuels have their own cold weather issues. But generally speaking, biodiesel fuels gel at significantly higher temperatures than regular, what we would call petrodiesel does. And that creates big problems for users of biodiesel in cold weather. So when you compare petrodiesel and biodiesel, you find that they can gel in similar ways and by similar mechanisms. As we said, diesel fuel gels because the paraffin wax content becomes insoluble at cold temperatures. These little seed crystal nuclei are initially formed, and then they grow and they adhere to each other, and they continue to grow in size, and they eventually form these large flat crystals that form a matrix that traps liquid diesel fuel in the pockets of the matrix, similar to kind of if you can imagine it, a fuel-filled honeycomb. Now, one thing that we'll touch on later is that when you start looking at this paraffin wax content in fuel, you can look at things like the distribution of the molecule sizes, or even the number of odd versus even molecule paraffin molecules that can influence how these crystals are formed. For example, odd and even number paraffins, like a paraffin wax that contains 9 carbons versus a paraffin wax molecule that has 10 carbons, odd and even number paraffins can have different enthalpies of formation, and they can form crystals at different times and in different ways in the fuel. Now, with biodiesel FAMEs, methyl esters, much of their gelling behavior comes from the saturated fatty acid content that's in the fuel. And these saturated fatty acids form crystals that then behave in much the same way as the paraffin wax nuclei of petrodiesel does. They form interlocking networks that trap liquid and end up thickening the fuel and causing problems. Now here we can see some close-up imagery of what this kind of wax crystal agglomeration looks like in the fuel. Now, as you can see this web structure that's showing up in the electron micrograph. You can see how these wax crystals have formed this intricate web that makes it very easy to trap fuel inside of it and to eventually cause a thickening problem inside or within that fuel sample. Now, if we know that biodiesel fuels gel at higher temperatures, then we would want to know next where the temperature range was that we might expect problems. If you're at all familiar with this topic, then you have likely heard or you're likely familiar with the three applicable temperature properties of fuel: cloud point and plug point and pour point. And each one of these temperatures tells us something different and something, we'll say something useful about the fuel and how the fuel performs in cold weather. Now, cloud point, the first one, cloud point is defined as the temperature at which enough wax crystals are precipitating out or becoming insoluble in the fuel such that the fuel becomes cloudy. You can see them. And as such, it is the highest temperature. It's the first temperature that the fuel encounters. Now, one thing to note is that when you're working with fuel, if you have a significant water content in that fuel, then you can actually get a false positive when it comes to cloud point, because some of that water, when it gets cold, some of that water may start to haze itself, and you can actually get a cloudy appearance in the fuel that's actually higher at a higher temperature than the fuel's actual cloud point. Now, the second temperature is plug point, or what they might call cold filter plug point. And cold filter plug point is the temperature at which enough of the wax has come out of solution that the fuel actually thickens enough to plug fuel filters and disrupt the fuel flow. Now, for regular, conventional petrodiesel, the plug point would typically fall about 10 degrees Fahrenheit below or after the cloud point. And then the third temperature, the pour point. Pour point happens last, and it is the temperature at which the fuel has gelled enough that it stops flowing and you can't actually pour it out of a given container. Now, there are, besides these three temperatures, there are other measurements as well. One of them you can see on the screen is low temperature filterability test, and there's also the cold soak filterability test. But given, generally these three temperatures, cloud point and plug point and pour point, those are the ones that are most commonly referenced. Lastly, with respect to the LTFT, the low temperature flow test, that's ASTM D4737, and the low temperature flow has actually become a lot more accepted within the industry within the last 15 years or so, and there are some people that consider it to be a better predictor of filter plugging in the field than the cold filter plug point test. Now, when you take these temperatures, or these temperature parameters, and you start looking at biodiesel fuel, the first thing that we notice, or rather I should say, when you take these temperature parameters and you start applying them and their meaning to biodiesel, the first thing that we notice is that B100, straight 100% biodiesel methyl ester, we notice that B100 has a higher temperature value for all of these measurements than most petrodiesels from the United States. B100 freezes, the parlance might be it freezes faster than regular diesel. In other words, it gels faster and at a higher temperature than regular diesel does. Now, when you go from B100 to a biodiesel blend, like, say, B20, which is 20% biodiesel and 80% regular diesel fuel, B20 gels at about between 2 and 10 degrees Fahrenheit higher temperature than regular number 2 diesel fuel does. And this is notable, not only does it gel at a higher temperature, but it also gels more rapidly. And this is because the pour point for biodiesel, remember pour point being the point at which it has gelled so much that it stops flowing, the pour point for biodiesel is usually only a few degrees below the cloud point. So there's much less difference or much narrower temperature range between the cloud point when it starts becoming cloudy and then the pour point when it is gelled and stopped flowing. There's much less difference in those temperatures than there is with regular petrodiesel. And that means that once the gelling process starts in biodiesel fuel, you go from cloudy fuel to gelled fuel much, much faster than you might be used to if you're used to working with just regular diesel fuel alone. Now, we will say that when we're trying to predict when biodiesel fuel is going to have gelling problems, a lot of that, or that answer depends a lot on the feedstock, what kind of fat or oil the biodiesel methyl ester was made from. Now, there are at least 13, here in the United States, 13 different but common feedstock oils and fats that your biodiesel likely comes from. And they all differ when it comes to cold flow performance. Now, without getting too much into the weeds of the chemistry of it all, we can note that a big determiner of some of the important properties of biodiesel come from the level of saturated fatty acids in the finished biodiesel. Now, when you look at feedstocks like animal fats, and also tropical oils like coconut and palm oil. In other words, the feedstocks that are down at this end of the graphic here, those tend to be more highly saturated fats. Animal fat, you think about animal fats, you think about lard, you think about tallow, those are associated with saturated fat. Now, on the other end of the spectrum, over on this end, you have fats and oils that come from plants like canola oil, safflower oil, sunflower oil, and corn oil. And these are not highly saturated. They have much lower content of saturated fats. They're more polyunsaturated and monounsaturated fats. And then in the middle, between the two, you have the soy and the peanut and the cottonseed. Now, the basic trend here, as you can see from the graphic, is that higher levels of saturation on this end, on the right side, the higher levels of saturated fat content give you a biodiesel fuel that, on the one hand, has pretty good storage stability, and it also has higher cetane value, but it has worse cold flow performance. It has higher cloud point temperatures, higher plug and pour point temperatures. And then at the other end, when you go to the ones that are much less saturated, the biodiesels made from these kind of feedstocks, they have worse storage stability, but they perform much better in the cold. Now, when we say that these are better in the cold than the ones at the other end, when we say that, how much difference are we talking about there? Well, for a B100 made from one of these plant oils, like let's say sunflower oil, a cloud point for a typical plant oil like sunflower oil could be, let's say, between 20 degrees Fahrenheit and 32 degrees Fahrenheit. Okay, that's okay. But if you switch to an animal fat or a tropical, a highly saturated tropical oil, you can be looking at, biodiesels made from these. You can have cloud points that are up around 45 to 60 degrees Fahrenheit, and that is a tremendous concern, especially if, as a user, it's not made completely clear to you what kind of biodiesel you're getting. There's a big difference when you're having to use biodiesel with a cloud point of, let's say, 45 degrees. If you have a biodiesel with a cloud point of 45 degrees, there's a big difference in how you're able to use it in, let's say, in Michigan in January versus if you're in North Carolina in September. And then, of course, if you're in a place like, let's say, North Dakota in the wintertime, well, all bets are off for any of those biodiesels because none of those are going to work there. So when you're starting with B100, how are you supposed to store and handle it to minimize potential cold flow problems? Well, a lot of these cold weather problems can be headed off if you're able to take precautions to ensure that the B100 doesn't get too cold. Now, above all else, you want to try and make sure that the B100, the temperature of it stays 10 to 15 degrees Fahrenheit above whatever its cloud point is. And this recommendation holds true whether you're distributing that fuel or whether you're an end user who's getting ready to blend it with your own diesel fuel to make an in-house, what we might say BXX blend, like a B2 or a B5 or a B20. Now, if you're distributing and transporting B100, you would want to use insulated tanker trucks in the winter. You would never want to use cold, uninsulated trucks because that just almost guarantees that you're going to have gelling problems with biodiesel. And whatever tanks and whatever pipes and whatever pumps that you use to move the fuel, those should all be heated and insulated to ensure that the B100 again stays at the recommended 10 to 15 degrees above the cloud point. Now, in terms of best practices for blending B100 with diesel to make a, let's say a B20 blend or a BXX blend, there are general guidelines that we would want to follow. The temperature of the biodiesel, you want to make sure that the temperature of the biodiesel fuel is either, 60 degrees is kind of a good ballpark, 60 degrees Fahrenheit, or 15 degrees above the cloud point. You also want to use inline blending procedures to ensure your best mixing. Now, if it's not possible for you to use inline blending, then the alternative practice is generally to take half of your diesel fuel and put it in the tank first, and then you would inject the warm biodiesel B100 at high pressure, and then you would follow with the other half of the diesel fuel. Now, one thing you do not want to do when you're doing any of this is introduce biodiesel B100 directly into a cold and empty tank because, again, like I said a minute ago, that just about guarantees that you're going to get gel biodiesel fuel. Now, if you happen to get crystals forming in your biodiesel, you can remedy that. You can get those crystals to go back into solution if you're able to raise the temperature of the fuel back above the cloud point. But again, depending on what your situation is, that may be easier said than done. Now, what about what we would call low blends? What about B2 or B5? That means they have a very small proportion of biodiesel in them. Well, the recommendations for those would be you keep them at 5 to 10 degrees above the cloud point of the blend. If you're able to do that, then as long as the diesel base of that fuel, as long as that diesel base is a good quality winter grade diesel fuel, then you should not need any other special provisions for storing or using that fuel in cold weather just because it has a small proportion of biodiesel in it. Now, this brings us to the issue of cold flow improver treatments for biodiesel. Now, when it comes to cold flow additization, most cold flow treatments, whether they're for diesel fuel or whether they're biodiesel specific, most of them work by acting on the crystals that form when the fuel gets cold. And they will do things to reduce the size of the crystals, or they will inhibit or alter how those crystals are formed in some meaningful way. Now, generally speaking, that, at least I should say from a conceptual standpoint, that's a different kind of control mechanism than the traditional old school method of taking biodiesel and just diluting it with number 2 diesel or even number 1 kerosene. When you just, let's say you add kerosene to biodiesel to try and raise its cold flow temperature up, well, that'll work to a certain extent, but the way that it works is it's a simple dilution method. All it does is it dilutes the fuel and it creates more space to keep those crystals away from each other. Now, the key thing to remember also about cold flow additives, again, whether they're for petrodiesel or biodiesel specific, is that they are rarely a single component item. Cold flow improver packages, they were called packages for a reason. They're usually a blended combination of ingredients, multiple items, that are all put together in this package to try and accomplish different important things to help how the fuel behaves in cold weather. Now, most cold flow improver treatments would start with some kind of vinyl acetate base. And the vinyl acetate base will work to address the behavior of the wax crystals in the petrodiesel part of the blend. Now, these work by modifying the structure of the wax crystals in the fuel, so that the modified crystal structures pass more easily through fuel filters, and they do not agglomerate, they do not grow as easily, and the net result is it gives the fuel better resistance to gelling. Now, if you have a fuel that's treated with cold flow improver, you want to make sure, or rather, if you have a fuel that you need to treat with cold flow improver, you need to make sure that you add the cold flow improver to the fuel before it reaches cloud point temperature. In fact, that's one of the most important takeaways, one of the most important best practice principles. You have to, cold flow improvers do not work after the fact. They have to be present in the fuel before the crystals form. So, add cold flow treatment to the fuel above the cloud point. So remember, we started with a vinyl acetate base. Then what chemists will do is they will start adding things like wax anti-settling agents, what they might call WASAs, and also wax dispersion components. They'll add those into the formulations. Now, WASA agents, they keep wax crystals suspended in the fuel and keep those crystals from settling out for extended periods of time. And so what you get is an end result where there's an even distribution of weights and sizes of paraffin wax crystals throughout the fuel, which makes the fuel less likely in the end to plug filters. In fact, as you'll see a little bit later, the distribution of sizes and weights of paraffin content in diesel fuel plays an important part in determining how that diesel fuel will gel and whether it's going to cause cold flow problems. In fact, here you see, these are some graphs of distributions by weight of the sizes of paraffin molecules found in various fuel samples. Now, all fuels will tend towards one of these kinds of distributions. So what you have here is you have paraffin wax molecules with certain numbers of carbons, 10 carbons, 11 carbons, 12, and then all the way up through to 25. Of course, the ones down here, because they have larger numbers of carbons, they are the heavier and larger wax molecules than the ones down here. And then you basically just got them all graphed by the amount by weight that these are in the given fuel sample. Now, this is a normal distribution. As you can see, it looks like a, kind of a nice even curve. You've got a lot of these middle ones. You've got less of the really light ones and less of the really heavy ones. It looks like a bell curve basically. You've also got what they might call narrow distributions, and this would be an example of a narrow distribution where there's an even higher proportion of these middle ones and even less of the two extremes. So even less of the really heavy ones and even less of the really light ones compared to the normal distribution above it. And so it ends up looking like a narrower, higher peaked a curve. And then there's also what they call skew ones, where the curve, the peak of the curve, so to speak, instead of being up here like in a normal distribution, it's skewing either towards the lighter end or the heavier end. Now, why do these distributions matter? Why do we look at things like this? Well, because if you can know the distribution of wax in a given fuel sample, you can predict how well a fuel responds to cold flow treatment. For example, if the distribution of paraffin in a given fuel has a greater number of heavy paraffins, let's say it's a skew distribution, but instead of skewing towards the light end, let's say that it actually looks like this, where there's more of these. If a distribution had more heavy paraffins, then that fuel, you say, well, that's more likely to gel at warmer temperatures because it has more heavy wax in it, and the heavy wax is the stuff that drops out or becomes insoluble and forms crystals first. Now, from a practical standpoint, it's more difficult to effectively treat a fuel that has a narrow distribution of paraffin sizes because the waxes will come out of solution at one time. There will be more wax that drops out within a shorter time period than if the fuel had a broader distribution, where you have a more even distribution of sizes. Those would tend to come out more, shall we say, more evenly over a given period of time. And if you have more of an even, gradual dropout of wax, well, that's easier for a cold flow treatment or a cold flow package to treat successfully than if you have some or all of the wax just appearing at just all at one time. So, as you may recall, wax anti-settling agents, that's what they do. That's their function in a cold flow treatment, is they take the crystals that have come out of solution, and they attract themselves to those crystals, and they treat those individual crystals and keep them suspended in the fuel. So if you have a more normal, even, gradual dropout, the wax anti-settling agent it's easier for it to more effectively do what it's supposed to do for wax that comes out gradually instead of all drops out at one time. Now, looking at skew distributions versus normal distributions versus what I call narrow distributions, if you compare those, that should also illustrate to us how difficult it is to make definitive predictions about how a given fuel will perform in cold weather. Like, what temperature will this fuel sample gel at? Even though skew distributions have, like in here, in this one where it's skewed towards the light end, even though this kind of skew distribution has more light paraffins than it does heavy paraffins, the simple fact that the distribution is uneven is the thing that makes it hard to treat for cold flow. So for fuels like this, if you have a wax anti-settling agent in the fuel, for a fuel like that, a wax anti-settling agent can actually take this kind of uneven cooling and precipitation of waxes and can actually make those waxes behave more like a normal distribution by keeping them suspended in the fuel, making their cold flow properties easier to treat effectively. So that's wax anti-settling agents. Now, what about the wax dispersant components, the second main constituent that they'll add in addition to the vinyl acetate base? A wax dispersant. Wax dispersants keep wax crystals apart. They keep them away from each other. And if the crystals are kept apart, then they will not stick together, and it makes it more difficult for them to grow larger and increase in size. So as you may expect, wax dispersant components work best when you pair them with wax anti-settling agents. And that's why you tend to have both of those in a good cold flow improver package. Now, for biospecific cold flow treatments, there's been a lot of research that's happened in the last decade that has seen certain kinds of components like polymethyl acrylate have some genuine value in treating biodiesel. They've done research, for example, on palm biodiesel, which traditionally has been extremely difficult to treat. You go back 10 years ago and ask a petroleum chemist, they would say, oh yeah, palm biodiesel, yeah, there's nothing you can do for it. There's not really anything that effective that you can do. But within the last decade, they've been doing a lot of research on it, and one thing that they found is that they now have certain kinds of components like polymethacrylates or methyl acrylates that have the ability to drop the pour point of a palm biodiesel by 6 to 8 degrees centigrade. That means even greater than Fahrenheit, 6 to 8 degrees centigrade, just by using small percentages of polymethyl acrylate in the formulation. Then another thing that we've seen happen in the last 10 years is what we would describe it as a differing ability to influence the cloud point versus the pour point of the biodiesel. Now remember, we talked about how there was a much smaller in biodiesel fuels. There's a much smaller difference or a much narrower difference between the cloud point and then the pour point when you're looking at a biodiesel fuel versus a petrodiesel fuel. And what this meant, you recall, is that biodiesel gels faster once the process starts because there's a much narrower temperature range. But in research studies within the last decade, what they have found is that some cold flow packages, they may not affect the cloud point as much, but they affect the pour point to a greater extent. And what that does is that widens the gap between the two. So they take B100 made from, say, mustard seed oil, and they formulate cold flow packages that seem to have no influence at all on the cloud point. They move it by less than 1 degree centigrade. But when they measure the pour point has dropped by 7 degrees centigrade. That is a significant and useful difference now. So one of the bottom line takeaways here is that it is vitally important to treat your biodiesel fuel for cold flow. We've established that, but what you have to keep in mind, and this is where we might differ from some other people, you do have to acknowledge that because of the inherent difficulties in accounting for the differences in feedstocks before the fact, if you have biodiesel and you're trying to figure out the best course of action, you really need to consider all of your options, and you need to be prepared that cold flow treatment is good. By cold flow treatment with chemical cold flow improvers are successful for a lot of fuels, but you should not always assume that that's going to be the best solution for you. You need to be prepared to consider all of the available options, including simple dilution and those hardware modifications, the insulation and the wrapping and the heating of the tanks and the pipes and the pumps. You need to be prepared to consider all of your options to make sure you have the best solution for you. And then the final point to make here, a couple of final points. If you have newer diesel vehicles, let's say that you mainly use biodiesel to run a fleet of vehicles on, and they're newer diesel vehicles that have common rail diesel engines. If this is you need to pay special attention to cold flow treatment of biodiesel in the wintertime. Now, what do we mean by this? Why did we have to point that out specifically? Well, the conventional recommendations, remember, we said if you knew what the fuel's cloud point was, then you could take, let's say 8 to 10 degrees below that. That would be what your expected cold filter plug point temperature would be. But the new advanced common rail diesel engines have changed this, and that's because of their high-performance fuel filters. The high-performance fuel filters filter particles to a much smaller effective particle size than the conventional or traditional diesel fuel filters. What kind of difference are we talking about here? Well, you go back before common rail diesel engines, and you might have a fuel filter that filters out 20 microns. Has an effective rating of 20 microns, and that was fine. That was spec'd for that diesel engine. Now you have a common rail diesel engine where it's spec'd for 3 to 5 microns. So you're talking about, let's say it's 5 microns. So let's say it's a 75% reduction. Well, that's a significant reduction in and of itself. However, as you can see, even a sizable reduction like that it's even larger than it might appear, and that's because of the mathematics of how these filter size differences play out. So as you can see here, what you have is a graphical representation of different comparison of different sizes. So the middle one here, this is your 25 micron size, and that circle, that represents the 25 micron size. And mathematically, you're talking about, almost 500 square microns of size. Now, if you were to go from a 25 to a 5, this is a 5. Now, first glance, you say, well, it's 80% reduction. That's pretty significant. But it's even greater than we think, because you're actually going not just from 25 micron effective size to 5 micron, but you're actually going from 490, almost 500 square microns to just 20. That's actually a 96% reduction. So the mathematics actually make it an even greater drop than it might seem. Now, what does this mean in practice? Why are we talking about this? Well, in practice, what this means is that fuel filters for common rail diesel engines, gel, will get blocked at significantly higher temperatures than before. And that means if you need to keep those kind of vehicles on the road, you need to take that into account. And so what they're saying is that the cold filter plug point temperatures for diesel fuel, if you're, diesel fuel or biodiesel, if you're using it in a common rail diesel engine, then the cold filter plug point, the effective cold filter plug point temperature for that fuel could be 5 to 8 degrees higher than it was before, because the filters are catching more wax and they're plugging earlier than they were before. So what they're having to do within the industry is they're having to rethink their recommendations. The fuel industry, it's apparent now that the fuel industry and the diesel engine industry needs to shift the conventional wisdom from telling people to worry about the plug point temperature to advising them now to treat the cloud point of the fuel as the new cold filter plug point temperature. So if you're in that industry, that is something that you definitely need to keep in mind. So that brings us to the end of our discussion of biodiesel cold flow issues. If you have any questions, my contact information is here on the screen. You have my email, ebjornstad@belperformance.net. Phone numbers on the screen as well. If you have any questions about this, drop me an email. Let me know that you were listening to the training presentation on biodiesel cold flow issues. If you had a question, I'll be happy to help you however I can. So that brings us to the end of our time today. Thanks very much for joining me. Again, I'm Eric Bjornstad with Bell Performance. Thank you very much for joining me, and have a great day.